In this video, I want to take a look at proof by contradiction. So for a proof by contradiction, we start with a statement that we'd like to prove. So for example, we might want to prove here that root 2 is irrational. And for a proof by contradiction, we start by assuming the opposite to our statement. So in this case here then, we assume that root 2 is rational. From here, we use deduction to show that our assumption is false, and therefore the original statement is true. Now, proof by contradiction is a powerful technique, and it allows us to prove many statements, such as, for example, the irrationality of root 2 and root 3, as well as there being infinite prime numbers. And that's only a handful of results that we can prove using contradiction. So what we're going to do here then is just take a look at some practice questions for proof by contradiction. Starting off with question 1 here then for proof by contradiction. So this question asks us to use proof by contradiction to show that there exist no integers a and b for which 3a plus 6b equals 1. So with this being a proof by contradiction here, what we're going to do to begin with is assume the opposite. So here, we're going to assume there exists integers a and b for which 3a plus 6b equals 1. Okay, so assume there exists. So assume there exists integers a and b So we have integers a and b for which 3a plus 6b equals 1. Okay, so this here then is our opening assumption. So what can we do next here? Well, with the 3a plus 6b equals 1, what I notice is I can just divide through by 3 here. If I divide through by 3, we're going to get a plus 2b equals 1 over 3. Okay. Now, if we just think about this equation here for a moment, a, we already know that's an integer based on this assumption here. Okay, so a belongs to the integers. Let's make a note of that here below. So a belongs to the integers here. Okay, so a belongs to the integers. 2b then, well, if b is an integer, based on this assumption here, then 2b will also be an integer. So 2b will also be an integer here. Okay, so 2b will also be an integer. So in that case then, the sum of a and 2b here, which is my left-hand side of this equation, that would also be an integer. Okay, so therefore, a plus 2b will also belong to the integers. Okay. And clearly then, you can see why we have now a contradiction, because we said then that a is an integer based on this assumption here. 2b will also be an integer, again, based on this assumption here. So therefore, the sum of a and 2b will also belong to the integers, because an integer plus an integer will give us an integer. Okay, all pretty standard stuff. So in that case then, a plus 2b equals 1 over 3. Well, 1 over 3 does not belong to the integers. Okay, so 1 over 3 is not an integer. And therefore, we have a contradiction. Okay, so we have a contradiction here. So like you can see, for this question here, actually forming the contradiction I don't think is too challenging. So just dividing through by 3, we get a plus 2b equals 1 over 3. A is an integer, 2b is also an integer, so the sum of those will belong to the integers, but 1 over 3 is not an integer. So a plus 2b here equals 1 over 3. That can't be true, okay, if a and b are integers. So what we can see then is the original question here, or this statement. So using proof by contradiction, we want to show that there exist no integers a and b, which 3a plus 6b equals 1. This must be true here because we've shown this contradiction, okay? So therefore, there exist no integers a and b, so there exist no integers a and b for which so we have 3a plus 6b equals 1 by contradiction. Okay. And there we have it. So like you can see, nice and straightforward, and that gives the solution there to question 1. If we just take a look now at one more question here for proof by contradiction, for this question here, we want to prove by contradiction that root 2 is irrational. With this being a proof by contradiction here again, what we're going to do is assume the opposite. So in this case then, if we want to prove by contradiction that root 2 is irrational, my opening assumption here will be to assume that root 2 is rational. Okay. So here we assume that root 2 is rational. Okay. We assume that root 2 is rational. So what does that mean then? If root 2 is rational, in that case then, if root 2 is rational, that means we can express it in the form a over b, where a and b are integers. So we can express this here as a over b, where a and b are integers. Okay, so where a and b belong to the integers here. Okay. And what we're also going to assume here then is that a over b is in its simplest form with no common factors for a and b. Okay, so also assume here so here we also assume that a over b is in its simplest form, so we can't cancel any further. It's in its simplest form here. So it's in its simplest form with no common factors. So with no common factors for a and b. Okay. So now, okay, with these two opening assumptions here, what I'm going to do to begin with then is square both sides. Okay, so I want to get rid of the square root here. So if I square both sides, then what I want to get is 2 on the left-hand side. And that's going to be equal then to a squared over b squared. So I get a squared over b squared. And what I'm going to do now is get rid of this fraction here. So to do that, I'm going to times both sides by b squared. So I get 2b squared. I get 2b squared is equal to a squared. Okay. So if a squared equals 2b squared, what that means then is a squared must be even. Okay. So this means a squared must be even. Because obviously my left-hand side here is a multiple of 2, so my left-hand side is even. So obviously, if these are equal, that means my right-hand side is also even. So if a squared is even, what that means then is a is also even. Okay. So this means a squared must be even, and a is also even. Okay. And this result here, you can also prove this using contradiction, and we're going to take a look at that in the exam revision video for algebraic methods. Okay, so don't worry about that for now. You might know this already, but if not, if a squared is even, a will also be even. Okay, and if a is even, then that means we can express it then as a equals 2n, where n is an integer. Okay. So we have a equals 2n, where n belongs to the integers. So if that's the case then, going back to this line here, okay, so if a squared equals 2b squared, and we know that a equals 2n, what I've got here then is 2n all squared equals 2b squared. Okay, 2n times 2n is 4n squared. What I've got now then is 4n squared equals 2b squared. Okay. And now if I simplify this here, dividing both sides by 2, what we get then is 2n squared equals b squared. So therefore, b squared equals 2n squared. Okay. So what this means then is b squared is also even because my right hand side here is a multiple of 2. So my right hand side is even. So obviously my left hand side must also be even because these are equal. So let me do this up here. So what this means then, so this means b squared is even. And again, you can see what's going to happen here then. So if b squared is even, b must also be even. Okay, so b is also even. But just think about this for a moment then. Okay, so if a is even, okay, so a is even, and b is even, can you see why this would form a contradiction? Okay, so if you think about this for a moment, if a and b are both even, then they must have a common factor of 2. Okay, so running out of room a little bit. It's not the neatest layout here for this proof by contradiction. So what I've done here then is just shrink everything just a little bit, just so I can keep everything on one screen, just so we can see a full consistent proof here for the irrationality of root 2. So if b is even and a is even, then like we said, this means that there is a common factor of 2. Okay, so let's just make a note of that here. So if a and b are both even, then they must have a common factor of 2. They must have a common factor of 2. Okay. And in this case then, this contradicts now our opening statement. Okay, so we assume that a over b is in its simplest form with no common factors for a and b. But like we can see here then, if a and b are both even, then they must have a common factor of 2. And that clearly contradicts then this opening assumption here. Okay, so let's just make a note of that as well. So this contradicts our opening statement. So this contradicts our statement that a and b have no common factors. Okay, so like we can see here, this contradicts our statement that a and b have no common factors. So therefore, the original statement here must be true. So in that case, then root 2 is irrational. Okay, so therefore, root 2 is irrational. So root 2 is irrational by contradiction. Okay. And there we have it. Okay, so like you can see, proving that root 2 is irrational is a little bit more complicated. There's a little bit more to it. But I think it follows in quite a nice structured way here. And I think it's quite intuitive as to why this contradiction forms. Okay, just showing a and b are both even. So therefore, there is a common factor for a and b. Like I said, I think that's quite intuitive if you just think about it for a moment. But either way, that's what you should get to here. And you should get then that root 2 is irrational by contradiction. Okay. And there we have it. So that's the solution there to the very last question. That brings the end of this video on proof by contradiction.